Welcome to Module 5 of the Milton-Madison in-depth web training. Module 5 focuses on the main span design and construction. We're pleased to introduce our speaker, Murray Johnson. Murray is Vice President and Project Director at Buckland and Taylor. He has extensive experience in the design, construction, inspection, and repair of bridges of many types, with particular emphasis on construction engineering, such as erection procedures, bridge lifting and sliding, lifting equipment, and other temporary works. Murray has managed the design, construction engineering, and rehabilitation of numerous bridge projects. He served as lead engineer for all temporary works and construction procedures for the main spans of the new Milton-Madison Bridge. Murray?
Good afternoon, everyone. So we're coming to the home stretch here now. I'll tell you what I can about the design and construction of the four-span continuous main structure. And then Charlie Gannon will be along to be the cleanup batter here with the exciting part, the construction. Buckland and Taylor's role in the design build project was as the designer for the main truss spans, and also the innovative construction engineering that was associated with that. My personal role was more related to the construction engineering, so I know a little bit less about the permanent design aspects. However, I'll try to cover that, some of the highlights of that with a few slides. You will see a bit of overlap with the other presenters, some of the photos and some of the discussion aspects. Try to be as unique as we can here. You have seen this picture before. This is the representation of the existing bridge and the artist's conception of what the new bridge would like when it came out for tender. The new design was mandated to be a truss, a continuous truss, to have somewhat similar appearance to the old one, pretty much right down to the color. Sorry, I just have to get my advance going here. A plan view showing the new truss design alongside the old one before it's demolished. So the bold lines in the top view show the plan of the new truss. Total of 2,427 feet from end to end bearings. That spans were from the left are 600 feet, 600 feet, 727 feet, and 500 feet. Now the span 2 and 3, that's one 600-foot span and 727-foot span, are the main navigation channels for the river, which are 2. In cross section, the truss is fairly simple and straightforward. We used a minimal amount of sway bracing in the design by making most of the sections rigid frames. Basically, the floor beams are rigid, connected to verticals, and that frame system is stronger, of course, at king posts where it passes over piers and transfers lateral forces from above down to the pier. Top and bottom lateral bracing systems, and a cast-in-place concrete deck supported on rolled stringers, which are in turn supported on welded floor beams. One of the joints shown of the truss node is at a bearing, so it's one of the larger joints. You can see a person standing there and get an idea of the size of the truss node. All of the truss members themselves are welded H sections. You can see a bottom chord H section and a king post coming up from the gusset plate there. And all of the connections are completely bolted, including stiffeners and gussets and angles within the joint. See, here's a couple of examples of a node and all the different parts that go into that node once connected. The floor system is continuous end to end of the bridge, so roughly 2,430 feet long, with no joints in the deck, and expansion joints only at the two ends of the bridge. So this means that the entire steel floor system had to float over top of the floor beams on bearings. So there's multiple bearings every time a stringer crosses a floor beam, and anchored only at the very middle of the bridge over the center pier. Bearings had to, well, they're large truss bearings, of course, this being a heavy truss. All the loads come down to single points. This bearing is between 5 and 6 feet square. There was some accommodation made within the bearing design to accommodate the sliding. That's what you're seeing in the bottom of this bearing. Bottom of the bearing in this photograph, you can see 4 inlaid panels of dimpled Teflon. That actually becomes the sliding surface that the entire bridge was slid over on the temporary piers and onto the permanent piers. I'll have a bit more on that later. Some diagrams to show you the basic construction sequence that was used for this 4-span assembly. The two river spans, the navigation spans, were constructed on barges against the Kentucky shore. Charlie will have more on this later. And floated out, then lifted up with strand jacks. And I'll go through all of that. So you can see that at the top picture where the first river span, 600-foot span, is being lifted up onto piers 3 and 4. After that, the shoreward span to the left is being cantilevered from that initially erected span until it reaches a temporary erection bent towards the abutment, at which point it's lifted up to take care of some of the droop that's occurring and can continue on to complete that span. Meanwhile, the other navigation span is assembled on barges, floated out, and lifted up into place. And then ultimately that other land span is cantilevered off of the erected nav span. You've seen this before, so I won't spend too long on it. Travis ran through this little sequence, but this is looking at the bridge in section to follow how the construction concept works. You can see the original pier and the existing bridge in position. We build our temporary pier, which I'll discuss further. Float in truss span, lift it up, clear of the lifting temporary towers, such that the sliding girder, which also forms a temporary pier cap, can be brought into place, and then the truss lowered onto that pier cap. Once in this position, once the deck is placed, the traffic is put onto the new bridge in this location, whereupon the existing bridge can be demolished, the existing superstructure, and the new pier cap's completed. Once all that's done, traffic's closed for a short while and the bridge is slid into its final alignment. And finally, of course, we take away the temporary works. So I'll discuss the temporary piers design and construction here. They're visible. A completed pier is visible in this view with the first of the spans erected on it and about 3 panels cantilevered already towards the foreground of this photo. Hopefully you can see my mouse. I'll try to point at some stuff here. Here's the rehabilitated stem of the existing pier. The tower, which comprises 6 36-inch pipe piles driven. And above water level, those convert to 4 legs for the tower, which is a braced tower on top of that. And at these 3 levels, we have what we've called barge impact frames, and I'll elaborate on those coming up. At the top is the sliding girder and temporary pier cap. And then we have 2 what we call stability frames, a lower stability frame and an upper stability frame. And really the reason for those is we did not want this tower to be completely disconnected from the permanent structure while we were undertaking these tricky lifting operations of these huge spans. So the purpose of the two stability frames is to maintain a connection between the temporary tower and the permanent concrete pier at all times. And the reason there's two of them is we have to lift the truss through, close a second connection, and open up another one, and I'll show that a bit more later. To the left of this picture, you can see in elevation view the top of the temporary tower and the little grillage that gets it focused on the panel point where the bearing is and where all the load comes down. It's worth mentioning that the load that's transmitted from the sliding girder during full design load during the temporary usage of the bridge coming through this point onto the top of this grillage and temporary tower is on the order of 11,000 kips. Pretty big load. So as I mentioned, the barge impact was a factor. Of course, the new bridge constructed in its temporary position and taking live traffic is subject to almost all of the design loads and constraints as a permanent bridge would be, with some minor reduction in wind load. But the barge impact provisions for the piers had to be met. And this is the type of barge train that you see frequently going up and down the Ohio at this location. And that resulted in several large frames being required to brace those temporary works and protect them against an accidental barge impact. Even though they're located on the downstream end of the bridge, the potential lateral impact from a barge drifting sideways and even an upstream impact had to be considered. You can see at the left-hand side of this picture there's a 48-inch nose pile, basically, as the first part of protection. And then all of the parallel lines there represent W24 sections in a big welded frame that is heavily stressed to the permanent concrete pier. That's a picture of one of those frames. In part, you can see it's not connected in the lower left-hand corner. That's because Walsh was also very clever to use it as a pile driving template for those 6 piles before it was connected to the pier, which at this point probably hadn't been finished past that point. At the other end of that, once it is connected to the pier, some fairly massive connections to transfer the loads from that frame into the pier. There are 3 of these. If you hark back to that diagram I showed you, there's 3 of these at different levels, and that's because the river level could fluctuate significantly, and did, as Charlie will tell you more about, during construction. We had to have a barge impact frame at each level, at different levels that would pick up potential barge heights. The main element of the temporary pier is the tower. This is the tower shown up to the very top. It's got the lifting frame sitting on it as well, which I'll talk about in a bit. And the first of the lowest of the barge impact frames is installed at this point. You can see it just above water level. Travis touched on the degree of reinforcement that had to go into the new pier concrete at this level where we connect our temporary tower, and so I won't talk about that too much more. It's another picture of it. And give you an idea of the scale of these towers or the amount of bracing in them. They're pretty substantial constructions. The lifting frames that were used at the 3 main river piers for lifting the 2 navigation spans basically continued the tower upwards for those last 2 panels. You can see on the left of this picture, had a small subcap on it, and then supported paired lifting beams which carried the strand jacks that would lift the span. So this is to get everything up and well above the points that have to be lifted on the truss. And then there was a small bent that carried the right-hand end of that lifting platform down to the existing pier. And you can see at this point we're starting to get pretty close to the old bridge superstructure. So there's a complete pier temporary pier ready for lifting. You can see the strand jack, the blue jacks up on top of the lifting frame at the very top, and the strands coming down, and then the strand loops up and goes over a rollover. So as you lift, the other end of that strand just keeps going over the rollover and goes back down towards the river level. But if you look at the two vertical lines that represent the strand jacks, that's the two truss planes. We have one pair of jacks lifting at each truss. And so then you can see, if you follow those lines down, you can see that on the outside of the tower, the outer truss has got a clear path upwards as it's lifted. The inner truss, the one closer to the pier, has to go up until it reaches that upper stability frame, and then the operation is halted. There's a lower stability frame, which you can see hanging right here on hinges, which is then swung up into place, connected to here. And once that connection is reestablished between the temporary and permanent piers, then this section is removed and the truss carries on through. So at all times we maintain a connection between the two. And there's just a view of the upper stability frame being connected after the truss has been lifted past. There's guys in the two man baskets there making those connections. You can actually see the bottom of the bearing of the truss above after it's been lifted past. The sliding girders are a very important component of this whole system. This is a girder already in place, installed, and with the truss lowered onto it. So basically complete at the top of the tower. Travis described the girders as kind of a tuning fork shape. You can see the main body of the girder, which is a box girder. And then this is one of the tines, we called them, of the tuning fork. And the other one is sort of just out of view. It's right here. The reason that was done was to leave the bearing portion, the final point of bearing of the truss on the pier open to be part of the permanent structure. So once we slid it over, the bearing was in its final position, and this tuning fork was branched around it, and after which it was removed and the pier cap completed. These are those sliding girders, all three of them sitting on a barge, 101 inches deep, 78 inches wide box girder with plates up to 2 3/4 inches thick. Each of these weighs close to 100 tons in its own right, and took a lot of care to fabricate and erect. They have heavily stiffened top flanges because the entire length of this girder will receive a truss bearing sliding along it with around a 4 to 5 foot square sliding footprint. You can't tolerate a whole lot of deflection within that footprint and still maintain your friction and the integrity of that sliding element. So there's quite a stiff top flange on these. If you look closer at the end of one of these box girders, you see 4 12-inch diameter pins, great big pins in a more or less square pattern at the end. This is on both sides of this girder, so there's 8 of these altogether on each girder. And this is what connected the tying girder to the box girder of the sliding girder. We had to pre-install the sliding girders up in the air, and you'll see this coming up, position them, and then raise our truss past the whole pier cap, and then bring the sliding girder in, position it next to the tying girders, and then draw these pins out into the tying girders, basically to make the biggest moment connection that I ever designed, and allow it to function as a continuous beam. So there's a picture of the sliding girders, the tines rather, pre-positioned up in the air. You can see the square hole right in the middle of the picture. Looking downstream there, that's where the sliding girder will ultimately be pushed in to pick up these 2 tying girders. I'm going to talk about a little bit about the span lifting. Charlie will discuss quite a bit more of the assembly of the trusses on barges, but this is basically most of a span assembled on sets of barges off the Kentucky shore. On the left-hand side of this picture, again, this is just a diagram of the completed lifting tower I showed you. And this occurred at the 3 main river piers. But of course, we're lifting 2 spans over 3 piers. After we lift the first span, we no longer have the center pier available to us. And we had to move off 1 panel point. So since this would already be erected and we couldn't have a lifting point here, we moved off 1 panel point and put the lifting platform and strand jacks at the top of this panel point. So that became basically the highest work point in the project there, I think. And lifted, there's the strand jack assembly here lifted at that panel point. And here you can see the 2 splices that were made here and here once the second span was erected. Some pictures of the span lifting. Those are VSL strand jacks on the left. 2 360-ton capacity jacks at each lifting point, so 8 total we lifted at the 4 corners. They came with up to a 22-inch stroke. And on the right-hand side, you can see the connections made at the bottom. The yellow steel is basically temporary works that's bracketed around the truss panel point to allow attachment of the bottom ends of the strands, which is at the top of that picture. A picture of the first span getting floated into place on the barges. This is a 600-foot span. And you can see here that it's what I described earlier. Here's the lifting plane of the outer truss. It's a straight shot down in. The floating span had 2 bottom chord sections cantilevered out from it because they're, of course, part of that node assembly. And it had to be maneuvered around the temporary pier. Everything was carefully checked ahead of time to fit. And then the connections were made here and here to lift it, and then similar at the other end. So it kind of came in like this and then backed up again to the other end until everything was in line with panel points. There's a picture looking down at the panel point. Here's the king post, which has had a splice added to it to keep it out of the way while we're lifting. So it wasn't assembled, installed at the time. And there's a picture of the span lifted to the first stop point, which is the point at which we swing up the lower stability frame and make its connection prior to disconnecting the upper stability frame. Keep in mind all the time traffic's flowing on the old bridge that's in the background there for the entire project. And here's just a picture of that first span after it's been cantilevered. 2 or 3 panels in the on the right-hand side, and after on the left-hand side, it's been cantilevered 1 panel or 1/2 of a panel, and the upper lifting platforms installed for the second span lift right here. Span 3 lifting is the second navigation span to go in, and here it's being lifted off the panel point, and here it's being lifted off a frame similar to the first lift. Sliding girder installation was a bit of tricky, very simple but tricky engineering in its own right. The crane was just capable of picking up the whole girder. But of course, if you have 1 crane and you pick up this big girder at the midpoint, we can only put it in so far, and then we have to disconnect the crane and get it in another way. So in this picture, you can see it just coming into position. And there's your 4 moment connection pins, and that end of the girder about to slide into the hole. There's a worker there. You can see the scale. And once it's gone in as far as the crane can reach, that is before the tackle starts to foul the structure, we basically blocked it off against the towers here and here and let it go. So it became a unconnected cantilever, basically, with an up thrust reaction here and a down thrust reaction here. At which point, workers could go out on the sliding girder and disconnect the crane. Oh, I'm going to jump just back to a picture of that sliding girder coming into the hole between the tines there. At this point, the worker has disconnected the crane. You can see the guys out here on the end of the girder. They needed a little bit of convincing to assure them that that was okay. but they eventually believed us, and they're out there reconnect the girder to the end of the crane to the end of the girder, and they were happy about it. Once that was done, the sliding girder was supported on the tail end by the crane while it was drawn into the tower on Hillman rollers, just using air tuggers. And once it was in position, which looks like that, the pins were connected to the tying girders and everything was buttoned up, and the truss could then be lowered on it. So in this picture, there's a lot of stuff in the way yet. Mainly the girder's been prepared where the bearing's going to land. It's been prepared by polishing it and greasing it. So it's covered with plastic and plywood to keep people from slipping. Once all that's cleaned out, then the girder would be lowered into position on top of the sliding girder. One of the aspects of the bearings on these trusses were that they were sliding free in all directions, and the permanent restraints for longitudinal and transverse loading, primarily wind, were separated. So there's wind shoes at the center of the pier floor beams with wind restraints on those, and at the very middle pier there's a set of longitudinal restraints. So here you can see the temporary restraints obviously had to be installed in order to use the bridge in its permanent place. In its temporary place, pardon me, under traffic loading. Just a couple shots of the side span construction. Once the river spans were erected, then they were cantilevered in because they're conventional stick-built fashion, one or two pieces at a time, lifted up and assembled in the air. With that, a 600-foot span cantilevering towards the shore will droop several feet. So we pick it up on the temporary bent in about the middle of that photo. And you can see it again in the right-hand side here, and then on the left-hand side is the jacking arrangement. So at the top of that temporary bent, there's an arrangement once the span has reached that point to jack it up such that when it reaches the end pier, the abutment, if you will, it clears the bearings and is able to land. So here's a picture just before. I've skipped over the deck and barrier construction. Charlie will be talking about that. So once the steel is erected, then of course all the concrete went in place, and at some point we put the traffic onto the bridge in its temporary position. So this is the stage just before the traffic shifted over. You can see it's still on the old bridge, but everything is in place for it to be shifted over to the temporary alignment on the new bridge. Again, Charlie will talk more about demolition, but this is the point at which the old bridge gets removed. There's a few impressive photos in there, I'm sure. And the pier caps, the new pier caps, can now be constructed with the old bridge out of the way, and line up with our temporary sliding girders. That pier cap construction, particularly the middle pier, which did the longitudinal guiding for the slide, had a lot of embedments in the tops of the pier caps, or both for sliding tracks and for guiding it. And here's some of the temporary works that the contractor had in place for that. Going to truss sliding now. There's a picture of the truss just before the start of the slide. So the old bridge is out of the way, the new pier caps are built, and the bridge is ready to slide over. A few numbers for you: over 2,400 feet long, confirmed as North America's longest lateral bridge slide. We're pretty sure it's the world's longest. 4 spans continuous, over 15,000 tons, and we moved it 55 feet. There's just a shot of what a top of a pier would look like with the pulling jacks. Just a little bit into the slide. The truss is already partly over the new pier. The same jacks were used that lifted the strand jacks, or the spans, up into place. Jacks turned sideways, 2 at each river pier and 1 at each end. There's a view of the sliding track, which is steel plate, polished steel plate, greased. lying on top of the pier, and 2 jacks in the middle of the photo there, and 2 strand bundles pulling at a river pier. Showed you this picture before. The sliding bearings had a the bearings themselves had an extra element added to the bottom, which was the erection sliding element, and that's these Teflon panels. We had grease tubes inserted in this bottom plate as well to help maintain grease levels as the slide went on. The sliding medium was simply greased Teflon sliding on polished mild steel, and so there's a picture of a sliding girder being prepared, surface being prepared by polishing. They would grind out any really rough stuff first and then polish it with some progressively smaller grits of paper on sanders to get a reasonable surface, polished surface to grease up. A little closer shot of the platforms hanging off the upstream end of the piers for the strand jacks and the operator there. And another picture of these pulling frames that are carrying the strand jacks. In this picture of the pulling frames, you can actually also see a bumper that's been installed with that letters P3 printed on it. That's Pier 3. That's basically the stopping point for when the slide was complete. Throughout the use of the bridge in its temporary position but carrying traffic, the bridge was articulating as it would normally, so that meant the bearings were released and able to expand the slide longitudinally and transversely with only the restraints, wind restraints, longitudinal and transverse in position. So that means that once the sliding was about to take place, all these free bearings had to be locked up in order that both parts of the bearing would come along for the ride. Here you can see sliding harnesses at one of the river piers with 2 bundles of strands pulling it, and underneath, and the round part in this picture is a dead end of a strand bundle, and you can see the sliding track underneath that's all been polished up because this has already passed by, and then there's pairs of heavy thread rods that are pulling along the second bearing. At the ends of the truss, where only 1 jack was used, just a slightly different arrangement, still a bearing harness, but a single strand bundle. VSL from Switzerland, who ran the slide and as well as the earlier span lifts for Walsh, had a system of laser targeting fed into a processor. Charlie will probably talk about it a bit more, that controlled the longitudinal locations of each of the 5 pulling points. And then all of that slide was controlled from a little booth on the bridge. Guys went along for the ride, basically with information fed into a laptop and controlled from a very simple panel. There's a time-lapse video here. In practice, we found this to be a little bit jerky. In your PDF version of this presentation, you'll find a link to the Milton-Madison website, where you can find this time-lapse video and several others to look at when you want to by yourselves. And here's the time-lapse. In the first half of this video, you're just looking at it from the side, obviously. Halfway through, we'll turn and look at it from the end, and it becomes a fair bit more apparent what's going on. And I see I'm almost out of time here, but I'm almost done too. Slide took place over 2 days. It was slid about 1/3 of the way, just about that bump there on the first day, and then they had to stop and make some adjustments for too much wind, and then it was completed on the second day without incident. There's a photo of the slide complete, and all that black steel on the right is now scrap. Basically, that's the temporary works. The bridge lined up. Took them a couple days after that to install expansion joints and grout them in place. A few lessons learned, since that's part of the process here. Try to develop construction schemes as far as you can, especially during bid design, before you have to commit to material order sizes. This is particularly an issue in design build where material orders go in very early and you don't have much chance to change them as you develop your construction scheme. Be prepared for potential rejection of modifications that may affect a permanent design, something you want to do to accommodate construction, and have a backup plan for that. We had one idea on embedding the sliding girders in the piers. It just wasn't acceptable to the owner in the end, and that meant for a bit of scrambling when it came time to design the sliding girders to accommodate that requirement. Friction can be too low as well as too high. We had designed for frictions that we were normally used to. We got unexpectedly low frictions on this. The guys did a great job polishing up the girders, and that meant we had to scramble right at the end to make sure that wind wasn't an issue when we were sliding. And although Travis said that big is harder to slide than small, that's true, but also I think no bridge is too big for a lateral slide if you get all your ducks in a row and do things right. A couple thank yous to Charlie and Walsh for some of the great photos provided to us, also Deborah Crawford as well, and Michael Baker for some of the graphics.
Okay, thank you, Murray. Such an impressive project. We'll now begin the Q&A session. We have received a few questions here. So one relates to one of your lessons learned on friction. What coefficient of friction was used?
Well, we've done this same sliding system before, greased Teflon on polished steel, mild steel, and recorded frictions around 6 or 8%. And that led us to design the slide for about 10%, although we made sure that nothing would fail in an ultimate way of below 15% friction. During the sliding, we recorded frictions down at around 3% from the system.
Okay, thank you. Next question. What is the estimated service life of the Teflon sliding below the end bearing that you showed, and did the design consider ways of replacing it in the future if needed?
That detail is, once the slide was completed, the slide is onto heavy embedded masonry plates anchored into the pier tops, and so the bearing ends up on top of those masonry plates, and the finished detail is basically a penetration weld all around the sliding plate, the bottom portion of the bearing, so that Teflon is completely encapsulated within that system and never exposed to the environment, and that system was accepted by the owner.
Okay, thank you. And then question, when lifting the trusses, what precautions or controls were used for the wind?
That's a good one. When you're lifting with strand jacks, it's provision for wind not unlike with the crane lift. You basically have restrictions on how high of a wind you want to lift in, and you don't start the whole process unless you have those or less winds predicted. With the exception that here it's a little hard to go back, so we did have contingency plans for wind. Structurally, there was no issue. The wind could have blown as hard as a design wind, and the system, all of the lifting system, would take that. But geometrically, there was an issue. As of course, as the wind blows, the span's going to swing sideways, and there's a point at which all those high tensile strands would start to foul parts of the assembly by which it was being lifted. And so our control was basically not to let that happen. And we had two types of restraint. One as an emergency lashing to the towers if unexpected wind came up during the lift and we had to stop. Then we had the means right at hand to lash the trusses to the towers, basically. And then one a little, once it got to the very top, there was one that was a little more organized to restrain it for a day or two while the tops of girders were being cleaned up and before you dropped it onto the sliding girders.
Okay. Well, thank you very much. We're out of time now, and we're at the end of the fifth 40-minute module. Thanks again to Murray Johnson and to all who participated in the fifth module. And again, Murray has also, as the others presenters have said he would be glad to take your questions directly if you have additional questions.